Okay, thank you for showing up. I hope you all have been enjoying the beautiful food. Okay, in this session, I want to walk you through our approach to a intrusion detect system of the IoT system. So just as the picture shows, we named it as IoT Woodpecker because we want to inspect the inner hardware bus of the IoT devices. As we probably know, the IoT world has a very severe fragmentation problem. In my opinion, it's basically it's a disaster of fragmentation compared with the fragmented Android world. So in this topic, we want to share our efforts, and hopefully this will give you some inspiration to make your own IoT ideas. Okay, then outline will be, first we will walk you through the IoT fragmentation and security challenges, problems, and then some basic principle of the IoT Woodpecker, and the prototype of it will be also introduced by me. And after that, we will share our analysis against the commercial off-the-shelf router. Then from that, I will transfer my podium to Dr. Xu. She will walk you through the efforts against with the artificial intelligence power. And after that, some scalable deployment of IoT Woodpecker efforts will be shared by Dr. Yang Bo. Finally, some future works and takeaways will be also introduced. So, as we probably know, the Internet of Things has a lot of fragmentation problems. In my opinion, there are problems from the standard fragmentation, the hardware segmentation, and from the hardware side, we have a lot of the CPU architecture, like the MIPS, like the ARM. And as for the story file system, we have a lots of like JFFS2 and SquashFS and UBI file system. And as for the characteristics, because we have a lot of IoT gadgets like the smart plugs and smart bulbs and also smart things. So the characteristics is also a fragmentation part. As for the operating system, we have Yocto, OpenWRT, the Android things, even the FreeRTOS. And the other fragmentation part comes from the manufacturers. So a lot of fragmentation, a lot of work to do, and basically the disaster of fragmentation. And this is a picture indicating the different alliance, the standardization organizations of the relative IoT landscape. So we have the home building, we have manufacturer, vehicular, healthcare, energy, and even we have the wearables and a lot of telecommunications standardization group like the W3C. And each of the logo means work, hard work. This is we extract some code from the open source HomeKit implementation called Homebridge. We found that there are 25 categories single in the home automation part. You remember the only home automation, we have 25 categories. We even have 125 characteristics, and we have 40 services. This is only come from a single aspect of home automation. So you can see the bridge, the fan, even the air purifier, the VOC density for the environment, for the air polluting monitor. So a lot of things to do. So this, as for another issue is what can we trust? Remember back in 1984, the C programming languages, the author of C programming language, the Ken Thompson, he wrote a backdoor in the C compiler in his class to show his students that you cannot trust the compiler. And each of the code his student wrote, when compiled with the compiler, will be inserted with a backdoor. So basically, Ken Thompson wants his students to know that we should know what can we trust and what can not be trusted. And for the year of now, 2018, what device can we trust? Because we have a lot of devices. We can trust the computer, or we can trust the hardware, or we can trust the chips. So we have to modify our trust level accordingly. So in my opinion, there are a lot of IoT security challenges, like we have limited computing, storage, and power supply capabilities of the device. We cannot install an agent on the, you cannot mine cryptocurrency with your Fitbit, right? So basically, we have very limited capabilities of the device. And second, there are various hardware and software architectures, which leads to the severe fragmentation disaster. And we have a lot of devices, huge number of devices, and they are always online, basically. And there are traffic between the device to the cloud, and the traffic between them also are encrypted, which means we cannot audit the HTTP or other plain text traffic. So there are a lot of security challenges. Therefore, the traditional solutions such as the monitor agents and the honeypot, I think the success cannot be easily adapted to this new IoT world. If you remember, in not so long ago, the Mirai, the IoT malware, they come up and cause a lot of trouble to the IoT world. Basically, the IoT is becoming the bottleneck of things. So the two of the solutions, the agent and the honeypot, has been, we have to do some modifications to help those methods to apply to our new designs, new world. So the previous work of the IoT honeypot in the year 2015, a group of Japan, a research group from Japan, they published a work called IoT Port. Basically, it's a very simple HTTP authentication method. During the 4 months the IoT port was setting up, they have, I remember they have captured 4 groups of different IoT malwares. But these are good days, the wild west of the IoT malware. And as of the year of 2017, a group of researchers from Palo Alto Networks, they published a project called IoT Candy Jar in the Black Hat USA 2017, remember? Basically, what they are wanting to address is the IoT malware is smarter and smarter. You cannot put a very, very simple honeypot and to capture them. So to summarize those challenges, we have agent part, we have fragmentation issues, and the constrained environment, and the encrypted traffic. And for the hardware honeypot part, we have the smart malware trouble. They have the simulator detection function. They can be honeypot resistant. So, and beside that, honeypot is not an answer for the system security. So it comes to our mind that since the adversary will be smart enough to detect honeypot, why not we directly use the original device in the wild? In our opinion, we think we should do the least modification to those devices to be a honeypot. All of our work will be based on this single one hypothesis. The inevitability of the memory accessing, which means if the attacker has bypassed a lot of the firewall, the social networking, and any other fancy things to get to your IoT devices. You have the malware, not me, the adversaries have to store the payload, the software, the malware in the memory, the non-volatile memories. So if it's not install those malwares backdoors, a simple reboot will solve each of the IoT problem, right? So based on this hypothesis, we build up a very simple prototype of the IoT woodpecker. Basically, we monitor the SPI traffic between the flash chip and the CPU. For example, for the wireless routers, we simply put a logic analyzer on the SPI traffic. And we wrote some code based on the SDK that the logic analyzer provides. We extract the JFFs and other file systems. We extract the file system log. So the basic principle of the storage system is not as fragmented as other things in IoT, because they are basically no more than maybe at least 2 or 3 different types of NVM. For example, they are SPI flash and they are NAND flash. The interface is on FI. They are enumerable types. There are no fragmentation problems. And as for the right, this is the timing diagram of the different, the 2 of the NVMs, the interfaces. So, like there are the SCK, the clock from the master, and the master out, slave in, and master in, slave out, and slave select. We only have to monitor those 4 pins on the chips. Is done. So they are, I think this is basically what we call the Achilles heel of the IoT intrusion detection, because you have a lot of types, devices to adapt. Why not we simply monitor the pins on the chips? It's simple enough, I think. So this is W25Q128B. It's a serial flash. The interface is SPI. And we can see we only have to monitor the SO and SI pin. And we connect it with a SPI probe, then we are good to go. And for this is another example of the NAND flash. Actually, the picture is the device here. It's commercial off the shelf. It's a router, wireless router. So the NAND flash is another story. It has a different pins, a lot of pins than the simple SPI flash pins. So we will give a live demonstration later. And as for the file system in IoT, there are also enumerable types of the NVM. Remember this, the only thing you have to know is that the file systems is a little different than the PC, like a computer file systems, because they have to deal with the very low price of the chips. So they have a lot of fancy technology like the read-only, the compressed file system, because now the IoT, the flash chip, may only has a capability of 4 megabytes. It's a very small one. So if you want to store a lot of things, you have to compress them before using. Actually, in some of the IoT devices, they will be decompress their whole file, whole data on the chip and read it into the memory, and then use. If anything should be added in the chip, which is quite uncommon, because a lot of the IoT devices, they don't have to write anything to the flash, right? So if they want to write something, there is a overlay FS, because we use the Squash FS. It is read-only. We cannot write anything. But if we combine the Squash FS with JFFS2, we can combine them with as a overlay FS. We can have both of them the benefits. So this is our first approach, the analyst against a very simple SPI flash the router. As you can see, this is the flagship. There are 8 pins. We only have to monitor 2 of the pins. And after writing some C++ code with the SDK it provides, we can extract a lot of the traffic, and we can get we can even get the file system log from this from this software. And to speed up, we tested the malware samples we get from the IoT port, because we help the Japan research group, the IoT port group. We help them to set up 2 of the forwarder. So they shared the malware samples with us. So we did a little simple test drive, and then we get a lot of the confidence, because with such a simple method on malware file signature, we get a very reasonable success. So then we are not satisfied with this, so we want to adapt our simple technology to artificial intelligence. From that, I will please welcome
here is okay.
PhD Congyuan.
After the data acquisition phase, finally we have got the signal on the hardware bus, and we consider all signals should be connected to the risk control system. Obviously, before we do that, it is not elegant to use human to analyze massive bus signals, just like the human body ATM machine. Fortunately, this is 2018. We have artificial intelligence. So, we try to combine this method with the traditional risk control system as a supplementary decision factor. We will introduce a deep learning-based method that can automatically and intelligently analyze the bus signal collected by the IoT woodpecker. First, let's take a look at the data flow. What does the data flow look like? The data flow consists of bidirectionally byte streams, and it's a natural NVM accessing log. Let's take in SPI as an example. This is a data flow that accesses 16 megabytes, which is always used in some routers. It's a SPI flash. This data flow is a bidirectionally byte stream representing the information on the mask output slave input MOSI and mask input slave output MISO data lines. Of course, we can use the SPI protocol parsers to analyze the meaning of these byte streams, but this is a more manual and not intelligent enough method. Our purpose is not to understand the access content of the file system, but to distinguish whether the behavior of the accessing operation is abnormal. So how we can do that? We coding them into images. Each pixel of the 8-bit grayscale image can be represented by 1 byte. In terms, 1 byte can be displayed as 1 pixel. The 8 figures shows the normal data flows and the data flows generated by the malware. We can see it by our eyes that there are significant differences. In fact, more than that, the difference part in these images are only a small part of all the differences. There are more differences hiding in the detail. The pictures are not clear enough to show all the difference. And even we have this large and cool LED screen, our eyes still can't distinguish the close green value. However, AI don't have this problem because it reads from the raw data. Here may be a question, why images? Because there is already a lot of progress in the field of computer vision. For example, both in the left side, both Microsoft and Google have claimed that researches on image recognition has progressed beyond humans, and this result are convincing because they use the ImageNet dataset with hundreds of object categories and millions of images. The computation has been running since 2010. The latest result shows that AI's classification score on ImageNet has exceeded humans. Another example is medical image recognition, which is the right picture. The two images on the right are examples of using medical imaging to detect an eye disease. There are subtle differences in the characteristics of the two images. Of course, I can't tell which one is healthy or diseased. The performance of AI in this area has reached the level of doctors with many years of experience. So we think we can use a neural network to do this and learn from the progress in the field of CV to detect malicious data streams. We don't design the model from scratch. We used it based on Inception V4. It was developed from the original Inception model. That is GoogleNet. It's called Inception V1. And after adding batch normalization, it's called Inception V2. After adding the factorization idea, it is improved to Inception V4. Then it is found that the ResNet can speed up the training. There will be Inception V4, which is this picture. Inception V4 is a complex convolutional neural network whose core is the three inception structure in the middle. All consist of convolutional layers. Basically, all the blue ones are the convolutional layers of different sizes, and the yellow ones are averaging pooling layers. We don't need to pay more attention about this because we made the following three improvements to Inception V4. First, this input size has been changed. Because the camera photos are color and has 3 channels, and our data are grayscale images, only one channel is needed. Secondly, because of the changes in the input, we have also do some corresponding simplification inside the Inception model. One classification task is simpler than the photos taken by the camera, so there's no need to extract too many high-level features. Last, the output function is replaced by a soft function into a sigmoid function, because we don't need to distinguish between images of so many classes. It's only need to distinguish between benign and malware data flows. It's a two-class classification problem. Then we just feed the data and do training stuff. We choose a DAM optimizer, which is based on stochastic gradient descent (SGD). The loss function is defined by cross entropy. In the loss function, theta is the undetermined parameter, m is the mini batch size, x and y is the training data pair. H theta is the model function defined by the parameter theta. And this is the training progress. The loss is decreased rapidly, and we got a good result. As a matter of fact, we performed nearly 1,000 tests on about 600 types of malware flaws, and the statistical results are shown in the figure. we got an average classification accuracy of about 82%, and the worst results are still over 71%. Therefore, we can see the detection method is robust and have a wide range of adaptability in detecting various types of malware data flows. The future work with AI, same as traditional deep learning. In the future work with AI, we need three more data, more powerful algorithms, and more machines. So we think a more scalable deployment of IoT woodpecker is needed. Towards the scalable deployment of IoT woodpecker, Dr. Yang will introduce these things.
Okay, good afternoon, ladies and gentlemen. Welcome to our session. In the previous slide, we have already introduced a new idea to detect the intrusion, but an idea which cannot be implemented or deployed easily would not be an idea practical enough. So in the following slides, I'll show our roadmap for the scalable deployment of the IoT woodpecker. So in our roadmap, there are 4 steps. First, the prototype that uses a logic analyzer to capture the data transfer on the signal transfer on the data bus inside the device, which has been shown already in the previous slide. And second, we add some real-time processing capability to the probes, which makes the calculation faster and simplify the whole system. And third step, we try to use some fast deployment gadgets, which makes the implementation easier. And the fourth step and the final step, we call it massive baseline observation. I'll explain that later. Okay, on the left side, you've seen that diagram before. That is how did we use a logic analyzer to capture the signals and analyze them. But when we need to make a massive, a more scalable deployment, we need to make multiple probes on multiple devices and get all the signals together, send them to a center woodpecker system. There could be 2 problems with this deployment. First, the cost would be very high because the logic analyzer isn't something cheap. And second, we have to gather all the signals and then process it. That means we cannot process the signal in real time. So if we are able to make the probes smarter, or to say, to make it able to do some real-time processing, this implementation may be much easier. So this is what we have done, that we made a real-time processing hat for the project. This hat is basically a CPLD daughter board for the Raspberry Pi. So why CPLD? Because, you know, with the components like CPLD and FPGA, the basic logic calculation in this chip can be parallelly performed and can be really fast. And also they have quite a lot of digital IOs, which is suitable for this application. And why Raspberry Pi? Because it has an operating system inside and it has the Ethernet. So within such kind of implementation, we can probe all the signals, process them, and report the suspicious events via the Ethernet port. And I just forgot to say that the most check or get the file fingerprint, something like that, some calculation like that are all bit calculations, which is really suitable to be performed in in a logical component like CPLD. And this is what we have done yet, and which will be demonstrated later. And you've seen this router before. In this demonstration, it acts as a victim, and we in this picture we have maybe it cannot be seen very clearly. These three jumper wires are ground, the read enable signal and the write enable signal of this NAND flash chip, and we get these signals out, get it to send the signals to the CPLD daughter board, and this is basically what we see. This is a read event, and that is a write event, and we can get several this kind of events. And each event will be reported to the Raspberry Pi, and the Raspberry Pi would record this event into the log. So if any suspicious event happens, we know something wrong. Something is going wrong. Okay, let's see the live demo.
So this is an iPhone, and I connect it with the. Okay.
Well, it is not just a camera, right?
This is just a camera. Yeah. This is the device Dr. Yang has designed. This is a CPLD head, and below that is a Raspberry Pi. We connect is with commercial off-the-shelf router, so maybe we can reboot it. Okay. This is our IoT Woodpecker demo, and I plug the router on. You can see some write event detected, and then we can wait for a moment. When the router is totally boot up, I think there will be other write events. Okay, I think if this is booted up, I will pretend there is some invader from the network side. I will connect, pretend I am the intruder. So I will connect the router with this iPad.
Yeah, you can just
to reconnect. Wait a moment. Okay, I think reboot is okay. Wait a moment. Okay, it's connected, and after then I will try to. Okay, I will try to connect the target, the IoT victim, through this. If you can see this screen, they are, after I logged it into with the SSH, there are some write event detected. I think this is because the key generation process. Okay, I just wrote a very simple demo to pretend I am write some payload. Okay, you can see this will be writing every 1 minute. Every 1 minute. Let's see, I can then 1 second.
1 second, right?
1 second. So
and there is also a LED blinking on the daughter board, which indicates the write event. Can you see that?
Yeah. So basically, this is our demo of the IoT Woodpecker, the first stage.
Yeah, if we can implement more powerful real-time processing capability into this probe, we can make more complicated calculations. Okay, the third stage Well, soldering all the jumper wires on the chip is not elegant enough, and it could be really complicated. So maybe some faster deployment gadgets should be used, like this the clips, test clips here. And the fourth stage, the massive baseline observation. In order to illustrate that, I'd like to invite everyone to watch this movie clip.
Oh, sorry.
Have you ever been in an institution? Cells.
Cells.
Do they keep you in a cell? Cells.
Cells.
When you're not performing your duties, do they keep you in a little box? Cells.
Cells.
Interlinked.
Interlinked.
What's it like to hold the hand of someone you love? Interlinked.
Interlinked.
Do they teach you how to feel finger to finger? Interlinked.
Interlinked.
Do you long for having your heart interlinked? Interlinked.
Interlinked.
Do you dream about being interlinked?
Interlinked.
What's it like to hold your child in your arms? Interlinked.
Interlinked.
Do you feel that there's a part of you that's missing? Interlinked.
Interlinked.
Within cells, interlinked.
Within cells interlinked.
Why don't you say that 3 times? Within cells, interlinked.
Within cells interlinked. Within cells interlinked. Within cells interlinked.
We're done.
Okay, this movie clip is from the movie called Blade Runner 2049, and in this clip, an cloned agent is answering several questions. Actually, he is being tested for avoiding that the cloned agent to have its self-consciousness. The basic theory behind this is if something goes wrong, or to say he has already generated his own self-consciousness, the reaction, or to say the answer to the questions would be different. Same thing, same theory can be applied, same theory could be applied to our devices. We can test the characteristics in the data bus inside the device and record it as the baseline, or to say as a reference, and set this device in a box and get it online. If something, so this kind of thing is basically acting as a honeypot. So if should anything happen, should there are some malwares or virus or something like that on the internet, this device should be infected, and we should be able to know that because we monitor the database inside it, right? So this kind of application can be used by the device manufacturer to monitor their own devices, their own products, and it can be used by security auditors. Okay, here's the future work part. So we're basically monitoring the non-volatile memory interface. We can extend such kind of interface to generous electric signals from the test point or from the printed circuit board inside the device. Maybe analog signal, maybe some other digital signals like the I2C, I2S, or UART, or something like that. And we can also monitoring the power signal using the set channel of the power line. We can monitor some calculations, characteristics in the CPU. And second point is automated optical inspection, because in order to implement this kind of monitor, we need to find the test points, or to know which pin of the chip we need to monitor. But actually, the chips are numerable, so maybe some automated way can be used. And using that kind of method also avoid the risk in the hardware supply chain. If your vendor, your manufacturer is adding something you don't want to the printed circuit board, you will be able to know that. Okay, the key takeaways in our presentation. The first, we proposed a novel intrusion detecting system for the IoT devices and verified and real devices. We state a hypothesis and verified it that the inevitability of memory accessing in hacking. And deep learning based artificial intelligence is introduced to detect the anomalies, and finally the roadmap of the IoT woodpecker. Okay, one more slide based on the idea for monitoring the hardware bus inside the device. We got some interesting findings in smart speakers, and this content will be presented tomorrow in a session called Auditable and Provable Privacy of Smart Speakers, also in this track. So welcome to join us tomorrow. Well, thank you.
Thank you very much. Are there any questions from the floor? No? All right. Well, if there's any other questions, I guess you guys will be around. So talk to them if there's any further questions. Thank you so much for your talk.